Hey there, let's talk about binary search trees. Specifically in this video, I want to help you define and identify what is a binary search tree. All the rules that go into determining whether or not something is a binary search tree, so you can tell that you're looking at one or whether you're not looking at one. We'll talk about some terminology, but keep in mind, I'm going to save searching and sorting and deleting and adding items and a whole bunch of extra stuff, especially the hard stuff, for videos that'll come right after this one. For now, we're just going to talk about what is a binary search tree. So you can see on the screen right here, I hope, that we have a binary search tree. Let's see, can you see that? Yeah, I think you probably can. Yeah, I think you can. This is not drawn quite as well as I would like to draw ours. I'll tell you how to do that in a little while, but when you draw a tree in a really, really nice, pretty, aligned way, it's way easier to debug. It's way easier to tell that you're looking at something that is sorted, and so forth. Anyway, okay, so first, let's start off with a graph. So this is not a video about graphs. I guess I can probably expect that you already kind of know what a graph is at this point in time, but for now we'll just say that a graph is a collection of nodes and edges. So what do I mean by nodes? Well, just imagine there's like a little circle here that contains some sort of data. If you know data structures already, then there would be a t-type sitting inside the node. We'll just call the t-type an integer. And so for our nodes, for our trees, we're just going to say that they hold integers, even though, technically speaking, in a binary search tree or a graph, you could have all sorts of different data types. Is this working? I think it's lagging. Okay. So I'm just gonna, grab this and sort of like duplicate it and just duplicate it again. I'm just gonna make a bunch of duplicates. Something is definitely wonky about my setup right now. I think I just upgraded the camera and the CPU is maxed out. I just upgraded the CPU on this computer too. Oh well. Okay, so we aren't going to support duplicate values in our binary search tree, but for now, I'm going to say it doesn't really matter for the graph. Later on, we'll start making sure there's no duplicate data. For now, I think I can probably do that somewhat quickly. Let's see, 7, 6, okay. So a graph, for our purposes right now, a graph is just basically a collection of nodes and edges. It could be empty. It could be just nodes. It couldn't just be edges. It would have, an edge always has to have a node or two connected to it. So we just have like a bunch of nodes. Inside of the nodes, we have t-type data values. This is a valid graph, but I'm going to draw some edges randomly here. So we're going to do this. It doesn't really matter. I'm just randomly drawing edges. Okay. Actually, I should probably do maybe like one that's kind of separated. Okay. So this is a graph. This is not a binary search tree. So let's add a bunch of rules. Let me just pull up my rules real fast here. Okay, so what is a binary search tree? First, we'll start off with the graph, like we have here, and then we'll say that the graph must be connected. What is a connected graph? A connected graph is basically a graph where every single node can find every single other node, or find a path to every single other node, only following along edges and only by respecting the direction of edges. You can see this particular graph is undirected, meaning the edges don't really have a direction to them. So that means we could travel along in any direction from node to node. So just as a real quick, I guess like tutorial, I'm going to say, is 8 connected to every single other node? Well, it can find a path to 12, and it can find a path to 33, and it can find a path to 76 and 45. But it cannot find a path to 99, which means this is not a connected graph. So that's the first rule that we have to implement here. We're going to say this graph needs to be upgraded or modified so that it will be a connected graph. So I'm going to basically just start randomly adding edges until this is a connected graph. I'm going to do maybe like an edge from 99 to 12 there. And then now I think this is a connected graph, but let's double check real fast. So connected graph. You know what? I'm going to put graph connectedness in another video to keep this one short. For now, check out my other videos if you would like to see whether or not a graph is connected. But long story short, as I just said, if every single node can find a path to every single other node without, skipping where there is no edge, then it's connected. Okay, so that's the first thing. The next thing that we need, let me just put the words connected up here. We need a connected graph. The next thing that we need is we need an acyclic graph, which basically means a graph with no cycles. What is a cycle? A cycle is, can you find a path in this graph that starts at one node and ends at the same node without repeating any edges? So for example, if I was asking, is 76 involved in any cycles? Well, we could go from 76 to 33 and then 12. And we could kind of take 8, 45, 12 again. But by the time we turn around and try to get back to the 33, we've already crossed this edge twice. So that means the 76 is not involved in any cycles because we cannot find our way back to 76 without repeating an edge. So 76 is okay. I'm just going to maybe put like a little checkbox here. And you can also tell that the 33 is not involved in any cycles because we go down to the 76 and then come back up to the 33. We already repeated an edge, so that's not valid. Same thing for going from the 33 to the 12 and then back again. Same thing for the 34, same thing for the 99. But if you look at the 12 here, we could actually find a cycle. We could go from the 12 to the 8, and then from the 8 to the 45, and from the 45 to the 12. Now we're back where we started. We're at the 12 node again, and we did not repeat any edges. So this is not acyclic. This is a cyclic graph. It's got a cycle. So that's the next rule we want to add. We want to make sure that our graph has no cycles. So the next rule I'm just going to say is going to be satisfied by me removing some edges at random. So I don't know, let's get rid of the 8 to the 45 connection, see if that works. Let's see. Well, wait a minute, what did I just do? Something happened here. I just accidentally, I erased too many edges from the last slide. Okay, let me add that one back in. 33 to 76, that was supposed to be there. So now we have an acyclic graph. And we can consider this graph a tree. The next thing we need to do is add a hierarchy to this tree. So this is going to make more sense in a little bit, but for now I'm going to say we'll imagine a family tree kind of. It's not really exactly a family tree, but imagine there are parents and children and grandchildren, and we'll just try to we'll try to rank children according to when they were born or how many parents or children they have, their descendancy, their lineage, whatever you want to call it. So I think I'm just going to maybe move the 8 up a little bit so that it's on the same rank with the 12 and the 33. So I'm just going to move these up a little bit and then redo their connecting lines. So I'm going to do this and that, and then we'll say that the 76 is still a child of the 33. So I'll just kind of move it over here. Or sorry, we never said it was a child. Now we're saying it's a child, because when you go from top to bottom, imagine like a family tree, we'll say we have parents and children. The children or the descendants are lower. The ancestors or the parents or the grandparents are higher. Maybe I want to put this 45 over on the left so that it's a child of the 8 node. And maybe I'll say that the 99 node is a child of the 12 node. Okay, so eventually this is going to look not exactly like a family tree, because usually in the family tree we have 2 parents that go to 1 or more children. In this type of tree, in eventually our binary tree, we're going to have 1 parent that has, children just by itself, like asexual reproduction. We're pretending to be bacteria again, or whatever. What was that comedy skit a long time ago? Tiny Elvis. And he was like, hey, see that protozoa over there? The thing is huge. Anyone? No? Okay. So the next rule we need is we must have a rooted tree. What is a rooted tree? Actually, let me clean up the lineage real fast, the heritage. I want to make nodes that have the same level with respect to their ancestors to have the same physical y coordinate, the same physical level. So notice how the 99, I just moved it down a little bit because I wanted it to look like it's the same, number of generations lower than the top row. So like with 8, it had a child, 45, so that's 1 level down. 33 had a child, that's 1 level down, that's a 76. And the 12, also 1 level down, would have been 99, but the 99 was kind of too physically high. This will help you debug your binary trees in the future. Anyway, so I'm just going to clean this up right now. And now that we have, parent-child relationships, we need to look at the most common ancestor in the whole entire tree, or if there is one. So notice how, I guess I'm just kind of using the word ancestor without explaining it. So your ancestors are the people that you're disappointing when you don't study for the final exam or for your work interview or whatever it is. Ancestors came before us, right? Like my parents are my ancestors. My grandparents are also my ancestors. My great-grandparents are also my ancestors. Going down in the family tree are your descendants. You know, my children are my descendants. My grandchildren are my descendants. My great-grandchildren are my descendants, and so forth. So if you look at the number 34 here, what is the greatest ancestor that it has? Well, if you just go up and up and up until you can't go up anymore, it's the 12. So that means the greatest ancestor of, at least in this tree, of the 34 is the 12. The 45, the highest you can go is the 8. Notice how 8 and 12 and 33 are siblings. There's not really like a parent-child relationship. They're connected sideways. We'll eventually get rid of the sideways connections for our binary search trees, but for now, we have some siblings, and so we actually have 3 different greatest ancestors in this tree. We've got 8 and 12 and 33, and that's no good. So the next rule that we need is we need one common ancestor for every single other node in the entire tree. So I'm going to duplicate this slide right here, and I'm going to say we need to clean this up. So we got to choose 8 or 12 or 33. I don't know. I'm just going to maybe say that 8 and it's 45 are children of the 12. So I'm just going to redraw a line here arbitrarily. So I'm going to go like that. Notice how I'm trying to keep the 8, the 99, and the 76 on the same y coordinate, the same level. Now we have 2, greatest ancestors. We need to have only one. So I think I'm probably going to say that the 33 and the 76 are going to become children of the 12 node, just for simplicity. So I'm going to put this over here. I'm going to get rid of that little line, and I'm going to like move this over here. This is a gross tree, but we'll fix it soon. We'll do that. All right. Okay. Okay, and then I have to get rid of that little sibling line, and then I have to add another line to say that 33 is a child of 12. Okay, so now we have a rooted tree. What we had before was an unrooted tree, or just like not a rooted tree, because there was no root. There was no greatest common ancestor to the entire rest of the tree. But now we can say that 12 is the root of the tree because it's the ancestor for all other nodes. I guess even if 12 was by itself, we could call it a rooted tree. It just wouldn't be a very good example. So I'm going to actually get rid of the word acyclic here since we already handled that. And I'm going to say that 34's greatest ancestor is 12, 99's greatest ancestor is 12, 33's greatest ancestor is 76. All the nodes in the tree, their greatest ancestor is 12, and it's common to all of them. So now we have a rooted tree. Maybe I should type in, am I doomed? I really hope the screen cast doesn't freeze. It probably will. I upgraded the CPU. It's 33% faster than it was before, but I didn't want to pay for a new motherboard, so I am still using an old CPU, even though it's new to me. Dang it, I'm going to have to spend like $500. Okay. So the next rule is, so we have a rooted tree, and now let's rearrange everything hierarchically, which we already kind of did. So there's not really much to do here, except let's see. Let's erase this. We did hierarchical organization. We probably just need to move on to our next rule, which is to say that if our rooted tree is to become a binary tree, then each node in the entire tree cannot have more than 2 children. Every single node in the entire tree can have 0 or 1 or 2 children. If there are 3 or more anywhere in the entire tree, then it's not a binary tree. So, okay, that means, the 45 is okay because it has no children. All the rows, all the leaves at the bottom are okay. All these nodes over here are okay because they just have 1 child. But the 12 node, the root of the tree, it's got 3 children, and that violates the rule. So now we need to rearrange this. So I think I'm going to just move these numbers down here, maybe. Maybe move these nodes just like a little bit lower so that we can have them become a descendants of the 33 node. So I'm going to do this. Okay. So cool. Now we have a binary tree, and now we need to rearrange the drawing a little bit. This is not part of the definition, but this will make it easier to debug your trees. So what I want to do is make it so that every left descendant of a node appears physically on that node's left side. So like, to the left in terms of the x coordinate. Every right descendant of a node should appear on its right side, or like further to the right on the x coordinate. So sort of similar to, like the y coordinate ranking. But notice how the 12, its left child is 8 and its right child is 33. So that means all the nodes here on the left side, that come underneath the 8 are left descendants, or you could say that they are in the left subtree of the 12. So they're okay because 8 is to the left of 12 and 45 is to the left of 12. But notice how 33 is a right child of 12, and it's part of the right subtree, it's part of the right descendancy, but it's physically on the left of 12. That's going to be really bad because it'll be harder to debug our trees later. So I'm just going to slide it over without rearranging the tree. And I usually try to split the difference here. So notice how I've got these two nodes here, and then their parent is kind of like physically in the middle. That will also help you debug in the future. So I'm going to do this. Wrong. Let me get the blue. I'm going to do this. Make sure that my ranking is still okay. Not the best, most neatest tree. And so now I'm going to look at the 8, its left subtree or its left descendancy. All of those nodes, which is just the 45, are physically to the left, so that's okay. Now I'm going to look at the 33. Its left child, 76, is the only thing that's on the left side in the left subtree, so that's all right. Probably the 33, I think it's still a little lopsided. I probably could have, dragged it a little bit more to the right, but I'm going to leave it. So the 33 and the 76 are okay. And then the 99 is a right descendant, or it's part of the right subtree of the 33, so it should be on the right side. It is, that's good. The 34 should be on the right side of the 33 because it's part of the right subtree of 33. It's part of the right descendancy. And it should also be on the left side of the 99 because it's part of the left subtree of the 99. So far this is okay. This is not the best drawing. So now we have a binary tree, and we have kind of drawn it in a slightly good way. Not super great. The last rule that we're going to add here is, whoops, what happened there? I'm supposed to do that, yeah. The last rule we're going to add is we must have ordering to our nodes, to the numbers in our nodes. So what do I mean by ordering? Well, the whole reason that we want a binary search tree, at least usually, is because it's really, really fast to search through. This is going to be a tree that we can search through in log time, which we'll talk more about in another video. We'll do time complexities and searching and stuff. But in order for this to be a super fast tree to search through, we need to be able to very quickly make a decision. Do we go down and to the left? Do we go down and to the right? And every decision we make should help us eliminate half of the remaining data set, half of the tree at a time, every time we go down a level. And that's only possible if the nodes themselves are ordered. So what I'm going to do is say, every node that's on the left side, or let's say every descendant that's on the left side of a node, should be of a lesser value than that particular node. Every node that is on the right side of a node, meaning it's a right descendant of that node or part of the right subtree of the node, should be greater than that node. Please note that this would not allow us to support duplicate values in our tree. You could use something like less than or equal to versus greater than if you wanted to support duplicate values in your tree. You could also change the T type, the template type, to a node from the data you wanted to store to a list. So every single node has a list inside of it, and the items in the list are just, the regular values that you wanted. There's a whole bunch of different ways you could actually do that. But for now, we're going to say our trees don't support duplicate values. So, okay, we don't support duplicate values, but we need, from left to right, the order needs to look sane. And this is kind of why we're drawing the tree in this special way. We're trying to make our tree really easy to debug visually. So check this out. The way we've drawn this, every single node has its own x-coordinate, basically. Notice how the 12, there's like, pretty much nothing underneath it, at least not directly underneath it. The 33, the 34, all the nodes, you can draw a straight line down from the node and it shouldn't cross over with any other nodes or edges. So that means now that we've drawn it this way and we've made sure that all the left descendants are on the left and all the right descendants are on the right, we could actually just scan our eyes from left to right and be sure that we are seeing an increasing order, or usually we say non-decreasing order, but since duplicates aren't allowed in this tree, we'll say an increasing order or an ascending order. So if we start at 45 and then we go to the right, we should see a higher number. So if we look at 8, 8 is a lower number. So this violates the ordering rule. This is not a valid binary search tree. It's only a valid binary tree. So sad. Okay, so I could, swap the 45 and the 8, or I could just increase the value of the 8 itself. I think it'll be faster for me to just increase the 8 value. So I'm going to make it 52 now. So we got 45, 52, then we go to the right a little bit more. It should also increase. So 52 should increase. I'm just going to randomly increase it to, 59, let's say. Then as we go to the right, we see another number here. It is 76. That already is increased from 59. So we don't need to alter that number. Then we go to the right one more time and it's 33. We definitely need to increase that because it's lower than 76. So I'm going to put 87. Then when we go to the right one more time, that's the 34 down here. That's definitely a decrease, so we have to increase it now. So I'm going to say 99. How about if I just do 92? Yeah. So now we have a 92 down here, and then if we go to the right a little bit more, there's the 99. And now we actually have a binary search tree. Let's just double check all the rules. First off, is this a graph? Yeah, there's nodes and edges. There's nothing weird happening. There's not like a edge floating in the middle of nowhere. Is this a connected graph? Yeah, it is, because every single node, if you followed, the edges, could find every single other node. Like the 45, it could find, the 92 node if it just followed all these edges. Notice again that these edges have no direction. There's no arrows on them. So we could go up or down in any direction we want. So that means the 76 can find everything else. And so this is a connected graph for sure. Okay, now that we have a connected graph, is this an acyclic graph? I don't know about you, but I can't find any cycles in the graph, right? Like the 92, it goes out, but it doesn't come back in. Same thing for the 76. If we went from the 76 up to the 87 and then took a right turn, we wouldn't be able to come back towards it without repeating that same edge. So this is definitely an acyclic graph. All of the nodes follow that rule. They're not involved in cycles. Is this a rooted tree? Yeah, there's only one common ancestor to the entire tree. It's the 59. It's the highest node in the entire tree, and it's common to all of its descendants. So let's see. I'm going to duplicate this real fast. The next thing is we arranged it hierarchically, and we added the terminology of, I think I kind of just tried to sneak this one past you, but we added the terminology of a left child and a right child. Right. We also added the terminology of a right subtree and a left subtree. Just to clarify what I mean, what do I mean by a right subtree and a left subtree? So imagine we're considering the 59. If we consider the 59, then the 52 is the root node of the left subtree of the 59 node. If we consider the 59, then the 87 is the root node of the right subtree of the 59 node. So the right child is basically the root of the subtree the right child is the root of a subtree of the right subtree. I think I'm getting muddled my words here. Okay. Anyway, so we have a little bit of terminology. The 59 is the root node. That's like the only node in the entire tree without an ancestor or a parent. So, okay, then we have a binary tree because every single node in the entire tree doesn't have more than 2 children. Notice how the 59 has 2 children. That's fine. If it was 3, that's way too much. 52 has 1, 87 has 87 has 2 children, 99 has 1 child, 92 has 0 children. So, okay, we're not violating that rule. So we definitely have a binary tree. And then we, kind of read from left to right. Let me write down the numbers this time for fun. If we read the numbers from left to right physically without kind of following edges or anything, we just scan our eyes from left to right, we can see that we have an ascending list. If we supported duplicates, it would be okay to just see a non-decreasing list. But we see an increasing list or an ascending list. Okay. Whoops. This is the slow part. Okay. Notice how the numbers increase from left to right. So this is actually a binary search tree. And I don't know about you, but I think I need to get a Snickers or something right now because this video has been going on for longer than I wanted it to go on. So We've defined a binary search tree. In future videos, we'll talk about how to add nodes into a binary search tree, how to build the tree, what's the time complexity of the tree in various operations, deleting nodes from a tree, terminology, like what are these nodes called, things like that. So anyway, thank you so much for watching. I hope you learned a little bit of stuff and had a little bit of fun. I'll see you at a later date and time. Just kidding. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.